Welcome back. In this lesson, we're going to take linear regression a step further. Up to now, we have predicted a value using just one feature, like using a car's mileage to estimate its price. In that case, the model was simply f of x equals wx plus b. But real-world problems usually give us more information than just a single number. For a used car, we might know the mileage, the model, the age of the car, and whether it includes extra features or upgrade packages. Each of these is a feature, so we label them X1, X2, X3, and so on. In general, if we have n features, we can write our feature list as x equals x1, x2, all the way to xn. And instead of one weight w, we now have a weight for each of the features. W equals W1, W2, and all the way to Wn. This leads us to the model for multiple linear regression. F of x equals W1x1 plus W2x2 plus W3x3, and so on, up to Wnxn plus b. All right. Let us now talk about vectorization, which is a simple trick that makes this calculation much easier and much faster. When you build learning algorithms, vectorized code lets you skip long loops and replace them with operations that run in one line. It's easier to read, easier to maintain, and it takes advantage of efficient math libraries. Instead of multiplying each weight and feature one by one in the code, f of x equals w1 x1 plus w2 x2, and so on up to wn xn plus b, we use the dot product of the weights and the input features plus the bias. This one line replaces an entire loop and performs the same calculation. The bonus? It runs much faster, especially when the number of features grows, and vectorized operations are optimized to run in parallel. Libraries like NumPy and scikit-learn are built to hand off these operations to low-level routines that can use the full power of graphical processing units, or GPUs. Let's talk about GPUs a bit. GPUs are physical hardware components designed to perform thousands of small calculations in parallel, originally for graphics and rendering. Vectorized machine learning code fits that pattern perfectly, allowing the GPU to process whole arrays in single sweep. The result is faster training, faster predictions, and code that scales when your data grows. All right, you've now seen gradient descent, multiple linear regression, and vectorization. Let's bring them all together and use gradient descent to train a model with multiple features. Instead of thinking about each weight as a separate number, we group them into a vector w and keep b as a single number. With this notation, our prediction becomes f of x equals w dot x plus b. Dot is the dot matrix. The cost function also changes slightly. Rather than writing it in terms of individual weights, we treat it as a function of the weight vector w and the value b. Gradient descent now updates every parameter in that vector. Each step adjusts w and b by subtracting the learning rate times the derivative of the cost. The idea is the same as the single feature case, only now we repeat the update for every weight in w. That is gradient descent for multiple linear regression. Let us implement this for our car price example using Python. Let's look at our data. Here is our training data set. Each row represents one car, and each column is a feature the model learns from. That is mileage, car type, encoded as sport, hybrid, or base, and the car's age. The final column is the true car price, which is what our model is trying to predict using these inputs. Great. Step 1 is to get everything ready to train our model. First, we import the tools we need. NumPy for data, Matplot library for plots, and scikit-learn for linear regression and feature scaling. Next, we create our training data. Each row in xtrain represents one car, and each column is a feature like mileage, car type, and age. Then ytrain stores the correct price for each car. Finally, we save the feature names so our results are easier to understand later. Now the data is ready, and we can move on to training the model. In step 2, we take care of a few important tasks before training the model. First, we check the shapes of xtrain and ytrain, just to make sure the number of cars matches the number of prices. Next, we normalize the features because some values like mileage are much larger than others, so scaling helps the model learn more efficiently. Now, we can train a linear regression model using gradient descent on the normalized data. Finally, we print out some details to confirm training worked, like how many iterations the model ran and how many weight updates it made. And that's it. The model is now trained and ready to use. In step 3, we look at what the model has actually learned and make predictions. First, we extract the learned parameters, the weights, which tell us how important each feature is, and the bias, which acts like a starting value. Next, we make predictions in 2 separate ways. First, using scikit-learn's built-in predict functions. Then we manually compute the same predictions using the formula, features times weights plus bias. We compare both results to confirm they match exactly. Finally, we print the predicted prices alongside the true prices to see how well the model performed. This confirms our model is working correctly and producing meaningful predictions. In the final step, or step 4, we chart true and predicted car prices for comparison. Each panel shows one feature, like mileage, sport, hybrid, base, or age. The blue dots are the actual prices, and the red dots are the model's predictions. When the red dots are close to the blue ones, it means the model is predicting well. You can see that the predictions follow the same overall patterns as the true values, even if they are not perfectly aligned. That's exactly what we want at this stage. The model has learned the general relationship between the features and price. Small gaps between the points represent prediction error, which we can reduce later with more data or tuning. Overall, this tells us the model is learning meaningful patterns, not just guessing. And that wraps up linear regression in supervised learning. You now know how models learn to predict numbers. Next up, we switch gears and learn how models make decisions, not predictions. We go back to classification. See you in the next video.